Hello and welcome to our session on teaching robotics and controls made easier. I'm Mada Lusoy, a mechanical engineer working with the controls and deep learning product marketing team at MathWorks.
And I'm Jennifer Gago, an industrial engineer specialized in robotics who works in the MathWorks academic group. In this session, we are going to highlight various tools and resources for educators teaching robotics and controls, including downloadable courseware materials, interactive examples, virtual labs, and much more. First, Melda will focus on the theoretical part of teaching robotics and controls. Later, I will talk about the practical aspects of it. You can download the presentation slides from the Handout section, and alternatively, you can access them on the Expo website.
Designing robotic systems is a multidisciplinary task that involves perception, sensing, planning and decision, platform use, connectivity, and control. To successfully design and develop robotic systems, we need tools that allow us to effectively cover all these areas. The director of the Autonomous Learning Robot Lab highlights MATLAB and Simulink to design advanced robotic systems, which includes design and simulation of controllers, automatic code generation, and data analysis and visualization, among others. Teaching robotics engineering requires a multidisciplinary approach reflected in the wide range of courses offered in a typical program. However, this can pose a challenge for instructors when designing content and activities for students. Therefore, this presentation will explore various tools and resources that can assist instructors in delivering a comprehensive robotics degree, with an emphasis on controls. Instructors face several challenges when teaching robotics and controls courses. One major challenge is time constraints that many of you might have experienced when developing a curriculum. Other challenges include to keep students engaged during class and find ways to facilitate independent learning. Hands-on learning is crucial for students as it lets them to apply their learnings from class to real-world applications. However, it can be challenging to scale access to resources for hands-on learning, especially when it comes to hardware resources. Grading student assignments and providing constructive feedback can also be difficult, particularly with a large number of students. Finally, it is important for instructors to provide opportunities for students to work on projects that push the boundaries of their understanding. To address all these challenges, we designed an agenda that incorporates different teaching activities, with each activity focusing on a specific challenge and proposing a corresponding solution. We will first start with preparation of the classes, where main challenge is developing curriculum under time constraints. In this section, we will discuss how you can use ready-to-use courseware to save time during course preparation. Whether you're putting together a new curriculum or want to enhance your existing one, you can explore ready-to-go teaching content that we have available on the MATLAB and Simulink courseware site. Resources you will find here are tailored to multiple disciplines, including robotics and controls, and include downloadable course materials, virtual labs, educational videos, apps, and project-based learning exercises, developed by both MathWorks and faculty from leading universities around the world. Next, we'll take a look at one of these teaching materials in more detail. There are many great curriculum materials developed by universities and shared broadly with the community to be used by instructors as well as students. Such an example is the control tutorials with MATLAB and Simulink, developed by University of Michigan, Carnegie Mellon University, and University of Detroit Mercy in collaboration with MathWorks. These tutorials facilitate self-instruction on various controls topics as well as the use of MATLAB and Simulink. You'll find a range of common control system related examples, and for each of the examples you'll find tutorials on system modeling and analysis, control design using PID, root locus, etc. Some of these tutorials are available in MATLAB live scripts, which we will discuss later in more detail. The LiveScript control tutorials let you interactively update parameters of dynamic systems and immediately see results as shown in the video clip here. They can also be run in any browser without the need to install MATLAB. To learn more about the control tutorials and how to use them for teaching controls, you can check out the webinar by Professor Richard Hill from University of Detroit Mercy. Next, we'll focus on lessons and discuss how to gauge students' interest during class so that they can get the most out of the teaching hours. In this section, we will highlight various tools and resources you can use to make your lessons more engaging and dynamic, encouraging students to actively participate in class. A great way for engaging your students is to use MATLAB LiveScripts. With LiveScripts, you can create interactive lectures by combining code and results with formatted text and mathematical equations. You can also insert images and interactive controls such as sliders, buttons, and drop-down menus. You can create step-by-step lectures and evaluate them incrementally to illustrate a topic. You can modify code on the fly to answer questions or explore related topics. Share lectures with students as interactive documents, and distribute partially completed files as assignments. For more examples, you can visit our LiveScript gallery and MATLAB file exchange for LiveScript examples authored by other instructors like you. Here we show an example of LiveScripts to explain complex concepts in robotics. The tutorials developed by MathWorks on the use of ROS with MATLAB and Simulink contain LiveScripts that take the form of 9 interactive lessons, 4 hands-on projects, and technical documentation to get you started with ROS and ROS2 in a practical way. The combination of theory with a graphical and interactive component promotes the best assimilation of concepts by the students. We encourage you to try this example, which is available on the MATLAB file exchange. Another tool for engaging students is apps. Teaching with apps allows students to become familiar with new theoretical content in a visual and practical way. With MATLAB App Designer, you can create interactive applications without having to be an expert GUI programmer. Simply drag, drop, and resize components and program their functionality. You can find apps designed by MathWorks, such as this example included in the Robotics System Toolbox, which shows an application that allows you to calculate the inverse kinematics of a robotic arm by simply modifying its position with the mouse pointer. In addition to apps provided by MathWorks, you can also find apps developed by instructors like you. On the left, you see an app developed by RWTH Aachen University to visually teach control design and frequency response analysis of systems such as mass damper and inverted pendulum. And the picture on the right highlights apps developed by University of Sheffield to teach fundamental topics in controls, such as dynamic system behavior and PI control design. You can find and download these apps using the provided links on the slide. Once you have interesting examples to show in class, you can facilitate their use by students by leveraging MathWorks cloud-based tools such as MATLAB and Simulink Online. With the online tools, you can run the latest version of MATLAB and Simulink in your browser without the need for downloads and installations. With MATLAB Mobile, students can follow along instruction on their mobile devices. They can create, edit, and run scripts and instantly connect results to concepts they're learning. You can collaborate and share files with students thanks to the 20 GB of cloud storage provided by MATLAB Drive. Now that we've seen various tools and resources to prepare and conduct our theoretical lessons, let's see how we can facilitate the study of these subjects for our students. In this section, we will highlight online courses and educational videos for self-learning of robotics and controls concepts. Onramps are free, self-paced online courses that students can take to get started with the basics of MATLAB, Simulink, control design, AI, and computer vision, among others. For the full collection of Onramps, you can visit the link provided on the slide. The online courses can be run in any browser and contain hands-on exercises as well as short video demonstrations. Students get instant feedback as they complete the provided interactive tasks. They're provided with a certificate upon completion of the online course. They also get a progress report that they can share with you so you can check that they have successfully completed the course. All these online courses contain practical tasks relevant to robotics and control engineering, as seen on the slide. A valuable resource for students to enhance their self-learning is the MATLAB Tech Talks, a series of educational videos that introduce various controls topics. Tech Talks use simple and relatable examples to help students grasp complex and abstract engineering concepts. With Tech Talks, we cover a broad range of subjects from PID control to reinforcement learning, and from body plots to learning-based control. You can access all existing videos and stay up to date with new videos by visiting the MATLAB YouTube channel and our Tech Talk library. So far, we focused on the lessons and self-learning resources for students. In the rest of the session, Jennifer will highlight the different approaches that professors can use for the practical aspects of their courses.
Thanks, Melda. We know it is important to complement the teaching of theoretical concepts with applied practice of these concepts in the laboratory. One challenge with labs that we hear from professors is to scale access to resources for hands-on learning, as lab activities involve hardware which can be expensive, especially classes with a large number of students. This section will show how you can overcome this challenge by using virtual labs and low-cost hardware to facilitate project-based learning. Starting with virtual labs, this example shows how easy it is to create a practical application from theoretical concepts shown in class. You can convert written notes on industrial robotics into a live script that defines and visualizes a two-link planar robotic arm and calculates direct and inverse kinematics. Then, students can learn how to model and simulate this robotic system using Simscape and use Simulink to understand how to use the inverse kinematic equations and the system's Jacobian to make the robot draw the work that we proposed. This simple hands-on application gives them a notion of the relevance of the contents explained in class to work with real applications and promotes creativity. Simulink is for model-based design as much as it is for simulation. You can use Simulink with other tools to design and simulate your systems to create virtual labs or before moving to hardware. For example, you can use Simulink with Roadrunner to design 3D scenes for automated driving simulation, or use Simulink 3D animation to visualize dynamic system behavior of robotic systems in a virtual reality environment. You could also set up a synchronized robot simulation between Simulink and Gazebo to send commands and receive data, or use Simulink with virtual Quansel labs, which are digital twins of Quansel's hardware for teaching robotics and controls. Simscape extends Simulink with tools for modeling and simulating multi-domain physical systems. With Simscape, you don't have to write more code to numerically solve systems of equations. You build the custom blocks, connect them graphically, and let the solver do its work. Here we highlight two virtual labs using Simscape developed by MathWorks. The one on the left contains a quadcopter model that can be useful to teach students about electric motors and battery modeling, mechanical system modeling, PID control, path planning, and how to use Python queries and perform a profitability analysis with MATLAB, among other learning outcomes. The Kalman Filter virtual laboratory on the right contains interactive exercises that let you study linear and extended Kalman filter design for a state estimation of a simple pendulum system. This virtual lab lets you visualize pendulum dynamics using 3D simulations and animations. Both virtual labs are available for download on the MATLAB file exchange. In addition to virtual labs created by MathWorks, on our courseware site, you can also find labs developed by universities. Here we are highlighting the vibration and control virtual labs created by the Kensho State University. Students can adjust the parameters of different virtual mechanisms and view the system response in 3D. They can study topics such as free and forced response of single and multi-degrees of freedom systems, mode ratios, and PID control. You can download the labs and customize for your own course. Designing and simulating systems is also important to try new concepts and visualize how they will work, which keeps students motivated and prepare them for a range of careers. Project-based learning with MATLAB and Simulink gives the students direct exposure to industry-standard software and hardware. Thanks to MathWorks hardware support, you can connect MATLAB and Simulink to hardware such as Raspberry Pi, Arduino, or Turtlebot to design, test, and verify robotic systems. Instead of writing thousands of lines of code by hand, you can automatically generate code to increase productivity, improve quality, and foster innovation. Once you are satisfied with your model, you can automatically convert algorithms into C, C++, fixed point, HDL, or PLC code for deployment to hardware. Hands-on learning with MATLAB, Simulink, and low-cost hardware means students create cool projects while building valuable expertise. Working with hardware has become a foundational skill for today's engineering students. Professors from Onramps University have built a comprehensive curriculum to cover 12 different engineering laboratory courses with the Arduino Engineering Kit. Arduino, when used with Simulink, enables students to develop algorithms that interface with a variety of peripherals and electronics for mechatronics and control systems. Students can develop software, implement algorithms as standalone applications, and tune parameters while the application is running. Evaluation is the practical way we become aware of how effective learning is being for students. You are likely giving homework, quizzes, and exams to your students that involve them designing a solution to a problem and submitting their work for grading in the form of MATLAB code. But as your class size scales, you may become overwhelmed with the volume of student work to review. In this session, we'll show you how you can use auto-grading to save time and provide immediate feedback to your students on their assignments. Your desk may look something like the image on the left, covered in stacks of student responses to a lab assignment like our PI controller example. Rather than take weeks to turn around written feedback to your students, you can use our auto-grading solution, MATLAB Grader, to convert those traditional assignments into web-based, interactive, and automatically graded assessments. Students get real-time feedback that they can use to improve their solutions and master the skill that you want, and you get access to grades and learning analytics to measure student progress and improve your assessment designs. And if you're using a learning management system or LMS to deliver other aspects of your instruction, you can add MATLAB Grader to your LMS so that the students are one click away from completing their assignments and you get their grades directly into the LMS gradebook. Finally, it's important to find relevant opportunities to invite students to apply what they've learned in class, challenge them with innovative engineering topics, and match their knowledge against that of other students. Let's explore the student programs that we can offer to our students to draw a direct line between their academic passions and a profession. MathWorks provides complementary software, training, and mentoring for competitions related to robotics and controls, such as the European Rover Challenge or the MathWorks Mini Drone competition. There are also competitions related to AI or automotive, such as the Formula Student competition. Students can win prizes and bragging rights while developing their programming skills in these disciplines. Students are transforming their accomplishments into scholarships and rewarding careers. The technical and leadership skills they built during their time as a student don't go unnoticed. 70 of the Fortune 100 companies use MATLAB, and these top businesses are looking to hire people with MATLAB and Simulink experience. In addition, this pair of student programs are excellent initiatives to motivate the student to learn about technology trends while becoming an important contributor to the advancement of technical computing and model-based design. Simulink Student Challenge celebrates the talent and creativity of students learning with MATLAB and Simulink. Students from around the world enter by submitting MATLAB and Simulink files or videos that showcase their projects. On the other hand, MathWorks Excellence in Innovation is a list of inspiring projects based on industry trends for your capstone, senior design projects, or final year assignment. Students can gain official recognition for their problem-solving skills from technology leaders at MathWorks. With these examples, we complete the solutions shown in this presentation. We have learned how to develop a comprehensive curriculum under time constraints with ready-to-use courseware, how to gauge student interest during class with interactive notebooks, cloud resources, and apps, how to facilitate independent learning with online training and tech talks, how to scale access to resources for hands-on learning with virtual and physical labs, how to optimize student assessment with auto-grading, and how to challenge students with innovative engineering topics with competitions and innovation projects. We hope you find these solutions useful and that you can apply them to your courses as universities such as the University of Mondragon are doing. Thanks to several years of applying project-based learning with MATLAB and Simulink in robotics and control engineering courses, professors from Mondragon University have been able to support low-cost practical projects, increase student engagement thanks to the possibility to use the tools anywhere and anytime, and receive positive industry feedback from companies that are hiring graduates who have practical experience with MATLAB and Simulink. As we wrap up this session, we want to leave you with a couple of call to actions. We encourage you to take the Teaching with MATLAB course, which helps you create engaging and scalable instruction with MathWorks online learning tools. Today, we talked about various control and robotics curriculum materials developed by both MathWorks and different universities. To find those resources and much more, please don't forget to visit our MATLAB and Simulink courseware page. And if you are creating a new controls or robotics curriculum and want to learn how MathWorks support curriculum development, you can contact us at the provided email. Thank you for joining us for this MATLAB exposition. If you found this content interesting, you are sure to enjoy the following sessions on interactive learning and LMS-based tools for educators.